Recording this nugget makes me sad. And what a great way to start, right? Well, let me explain. So this is the first nugget in the brand new Cisco CCNP 2015. So if you want to know where did it all start, right here. And so I'm getting ready to record this video, and I go, okay, what technologies are we going to talk about? Okay, technology connecting offices. What do you got, Cisco? Let's see, we got MPLS. Looks like DMVPN, VPN. Ooh, a lot of DMVPN. Good. Okay, that'll be good. And then Metro E. Where's the T1 lines? Oh, there they are. They're still, okay, they're there. They're just really little now. You know, it's kind of like the world is turning, and it made me go kind of retrospective and think about my Commodore Amiga and running a BBS off a 1200 baud modem. And I'm like, I bet you most people don't even know what a modem is. You know, and like those kind of thoughts are shooting in my head. It made me sad. But nonetheless, it is a very exciting time to be alive because a lot of things are happening and how our offices are connecting. So think of this nugget. This nugget has one major goal, and that is to inform you of how we are connecting our offices in today's standards, because that will lay the foundation of how we build the routing for all of our offices, which is the focus of this entire series. So two major topics: what technologies do we use, and how are we doing the addressing? Here are your do I know this already questions. So pause the video, read these questions. If you already know the answer, then you probably don't need the information in this nugget, and you can move on to the next one in the series. Otherwise, let's get started. When you move from CCNA to CCNP, one of the big differences you'll notice is the size. Meaning, CCNA level 1, 2, 3 offices in an organization. Again, not to say that's all they can have. I'm just saying that's usually what the CCNA is about. When you move to CCNP, it's gone national, many offices, or global, worldwide connections. And when you're looking at those kind of organizations, you have to say, well, how are they doing that? How are they connecting their different offices together? Here's your gambit of options. Number one, direct connection. Direct connections, just like I was mentioning before, is the little T1 line. Or essentially, you're saying, I'm going to have a connection directly from one location to another. Now, when I say T1 line, that is a misnomer. Because T1 is just a measure of speed. It could be a frame relay, could be a DSL, could be a cable modem, could be, this whole gamut of options of connectivity. So T1 equals 1.544. How that's delivered when people usually say I have a T1 line is CAS or CCS. Very reliable. Telephony technology, actually, originally designed to carry phone calls, but tweaked to carry data. So extraordinarily reliable, but very small bandwidth amount, right? Problem with direct connection. And the reason that on that first opening I said it's very little, it's going away, is because they're not very flexible, they're expensive, and they're low bandwidth. You really pay for the bandwidth, how much bandwidth you want on that connection, and the distance. The further apart they are, the more expensive it is. Now, I just actually did a quote for one of my customers for a T1. The prices have come down, and I just give you an example. I'm going from Arizona to California, and we did a quote for a Direct Connect T1. It ended up being $368 a month. I'm not going to share the carrier that was with, but that was essentially, now if we're looking at the globe, if you're not familiar with the United States, it doesn't look like that. But over here is California, here's Arizona. They're right next to each other. So if I were to go from Arizona to Michigan, I would probably say that cost would be close to double. We'd be in the $500-$600 range. Just to give you an idea, for that 1.544 megabits per second. I always like throwing a couple dollar values in there because I know some of you are like, well, how much? That's kind of just a general guesstimate value, right? So direct connections, expensive, very reliable, not flexible. It's point-to-point connections, right? Packet switching was the darling of the industry when it was first released. And when I say packet switching, I'm talking again about private X.25, frame relay, ATM, those kind of connections. And we can also say MPLS, but MPLS is, I'll explain that in just a second. Let's just stick with those technologies right there. These are essentially same kind of model, just scribble that out and put frame relay, right? To where now you have the flexibility to connect to multiple sites because you buy one physical connection. So I'll say I'll buy let's do a committed information rate of 5 megabits per second. comes in on a serial cable to your office, and then you dictate which connections you are going to have through this service provider managed cloud. So again, we're not talking internet, we're talking private. And let me just add a quick 30-second snip on that. VPN. When I say VPN, most people go, oh, internet, encryption, tunnels, that kind of thing. All of this, I'd say almost all of it probably is a VPN, because what is it? It is a virtual private network. You and I do not own the cables going from my office here in California to an office in Arizona, or I just did those backwards, vice versa, right? I never pulled out my shovel and trenched the cable, so what do? I pay a service provider $368 a month to use their cable. So it's not my cable, so it's not private. It's not a PN, right? But I'm trusting the service provider that I'm paying that money to, that they're not stealing my stuff, right? Different levels of trust that you can have. So it's a virtual private network. So when you say VPN, it really encompasses all these kind of things, right? So packet switching is where essentially we have more flexibility, we have less cost than just a straight up direct connection, which is why those technologies were so great, but even those are fading away. Metro Ethernet, what is that? I don't know if you've noticed lately, but service providers are digging up streets all over the place. Maybe you haven't noticed, but maybe you've seen construction barriers and you're like, oh, they must be expanding the road. Chances are good they're not just expanding the road. They're actually, while the road is torn up, shoving bundles and bundles of fiber optic cable into the ground, because that's what they need to reach the bandwidth amounts that the world is demanding nowadays. So there's thousands of strands of fiber through each metropolitan area, and so the service provider leases that out. Some people call that dark fiber, but you have to say it that way. Dark fiber. Star Wars, got to get involved somewhere in there. So dark fiber essentially just means fiber that the service provider isn't using for their stuff. So what do? They lease it out to people, and they call it Metro Ethernet. And in a nutshell. Now, obviously, it's become far more of a bundled service offering than, oh, hey, we have some cable we're not using. You want it? You know, it's not that kind of thing. There's a service offering with that, but essentially, it is, I'll call it quasi direct connection within a metropolitan area where bandwidth is very flexible. You can increase, into typically the gigabit connectivity, and the price is very reasonable because it's, again, using fiber optic cable just within a metropolitan area. Now Metro Ethernet has stretched beyond. Cities are lighting up fiber strands to each other to where I can go from Phoenix, for instance, to San Antonio, Texas on a fiber optic Metro Ethernet connection. Now, those are close to 1,000 miles away from each other, but there is fiber run between all these little points of presence on the way. So Metro Ethernet means metropolitan area. Like, you can't go to a farm usually in the middle of nowhere and get those kind of connections, but metro area to metro area, like Phoenix to San Antonio, Texas, totally works. MPLS. Probably the most confused technology out there. MPLS is actually a service provider technology. What it is just a tagging mechanism that they can use internally inside of their network to differentiate different customers' traffic. It's just, for some reason, this analogy immediately comes to mind. You ever go to Home Depot and you see those shims, those little wood things that you stick under, like you got your refrigerator where one side's shorter than the other and it kind of rocks back and forth, right? Well, you can take one of these shims and kind of jam it in there, and now you've got a refrigerator that doesn't work. And my wife hates shims because I stick them everywhere instead of actually solving the problem, but they work well. Well, MPLS just puts a little shim in the packet that says, hey, I've got a tag of 5592 on this packet, and the service provider can then tag all customer traffic and isolate it from each other using these tags called, and that's what they call MPLS. Now, that phrase has started bleeding out into the enterprise community because the service providers use that as common lingo, and so service providers or enterprise customers are now going, oh, I need an MPLS connection, not realizing they don't actually deliver MPLS to your door usually. And MPLS isn't even a connection type. I can't go say I want to buy an MPLS cable. Essentially, you can take a frame relay connection, take packet switch. You can take a direct connect T1 line into that service provider. You can take a Metro Ethernet connection and bridge it into that service provider, and they can tag all that traffic. They can stick that shim in all your packets, and now it's called MPLS. Does that make sense? So MPLS is just a way that you can essentially use the service provider network like your own and connect everything on all these different connection types that are coming into. So all these different physical connections can bleed into a common logical connection within the service provider network. So what's the difference between L2 and L3? L2 MPLS is essentially the service provider saying, you know what? Here's your cable. Good luck to you. You can do whatever you want with it. So if you've got these 4 offices and you want to connect them all together into this MPLS network and have them all, maybe take your routers out if it's possible from a physical perspective and just plug them all into a switch, you could have one big switch network and put VLANs through the service provider, all kinds of different stuff, weird anomalies like that. You can do that. It just becomes like, if I were to draw it, layer 2 MPLS looks like this. The service provider just became a switch with 4 ports. 1, 2, 3. Well, I'm pretending this is an office. 4, right? And now you have this switch in the cloud. Service provider does not interact with you at all. Layer 3 MPLS is where the service provider talks to you, as in you see them as an endpoint and exchange routes with them. So if we were to expand this out, here's your router connected, however, this is the big question mark, at frame relay, T1, whatever, to the service provider router, and you can actually run a routing protocol, and that's usually, by the way, BGP, although others are supported by some service providers like OSPF and all that. But you run a routing protocol and exchange your routes with the service provider. They use a little virtualization magic, a VRF instance is what it's called on their routers, to kind of isolate your routes from all the other customers that they have. So you kind of have your own little world in the service provider. And essentially, they become an endpoint. So they are a layer 3 endpoint that participates in your private routing table. Weird. Hello. Weird. Because we have a service provider, which we kind of trust, but we're like, here's my routes to my internal network. So again, if this were we were having this conversation 10 years ago, I'd be like, oh, no way, we don't trust that. But this has now become very commonplace. And obviously, there's a trust level with service providers that's increasing every single day. So that's the difference between those two, VPN and DMVPN. VPN, as I'm referencing them here, is not going to be the kind of VPN I was talking about before, where internet traffic encryption, although it could be. But I just bite my tongue. That's not at all what I want to say. So what I just said, ignore it. VPN that I'm talking about here is not the kind of VPN I was talking about before, where I'm talking about all these kind of connections, saying those are VPNs too. They are, but I'm talking more about the traditional usage of VPN here, where you have the internet and you have an encrypted tunnel that's going between your sites. VPN is becoming more and more popular. Why? Because internet connections are cheap and getting cheaper by the day. More bandwidth, less money, it's just becoming the commonplace thing. And so what people are saying is, okay, I've got my office in California and Arizona, and I can get a 1 megabit per second dedicated connection for $368 a month, or I can buy an internet connection that's like 50 megs down and 5 megs up from my local cable or DSL service provider for $200 a month. Let's do the math. Now, what's the difference? Why would I get that 1 meg for 368 and 50 megs for 200? 50 megs is best effort, non-guaranteed service, but it's pretty good. It is. I mean, really. I know some people, well, they oversell. They do oversell it. But at the same time, yeah, I mean, if you are getting 1 on there, which you've got 1 dedicated here, if you're getting 1 on there, you're calling the service provider like, this is unacceptable. And I've dealt with a lot of these kind of connections, and they're actually getting better and better. Not guaranteed like this one is, but for a lot of companies, they're like, that's a pretty compelling argument, $200 a month. Why don't I just buy 2 of those, 1 DSL, 1 cable, for about the price I'm paying for a 1 megabit per second, and now we got a little redundancy. Does that make sense? Yeah. So people are starting to go VPN, connecting their office using these kind of connections. They don't have to, but that's commonly what's done, to bring up site-to-site VPNs and bridge those together. Now, what's this guy? Well, you can imagine the bigger and bigger this grows, the more headache it is to keep up, because every time you set up a VPN, you've got pre-shared keys on each side, or you have to introduce a certificate server, static IP addresses. I have to do a connection from here to here, connection from here to here, connection from here to here, and then start meshing these guys together. You got another office, mesh, mesh, mesh. It just starts going crazy. Right? So you go, no, back up. Let's have this go dynamic. Dynamic multi-point VPN allows these guys to automatically create VPN connections between the different sites. So here's your head office. Everybody establishes a connection there, and in a nutshell, this guy starts being the informer. He's like, hey, I know you're kind of going through me to reach that one. That's inefficient. Why don't you establish a direct connection out? Again, I'm imagining this is an office, not these remote roaming users. But why don't you, regional office, establish a direct connection down here with this guy? Here's all the information that you need to do that, router. Here's all the information that you need to do that, router. And these two routers are like, sweet, thanks. And they establish a direct VPN connection, now going direct instead of tandeming through this hub site. I know it got pretty messy pretty quick, but that's the concept of DMVPN. Well, let's move a couple layers up the OSI model to the network layer and talk about how these organizations connect to each other logically. IPv4 and IPv6. IPv4 currently rules the world as we know it. And you know what? And let me just talk about the thought that just shot through my head. We're now moving into the beginning of 2015, and I just thought, oh, this is a new update. This is going to be around for 2 or 3 years. What if that statement is inaccurate 2 or 3 years from now? Because IPv6 will rule the world. Like, that's the kind of transitionary phase we're in. IPv6 is taking over the world by storm, and I don't think people know just how fast it's moving. Why? Because IPv4 provides 4 billion or so addresses. First off, 3.7 or so billion of them are actually usable, meaning public address that we can use on the internet. So you start thinking, okay, 3.7 billion devices, there's a whole lot more, because we're in this world called the Internet of Things. This picture is far more than just fodder. What's the biggest things that happen in our world today outside of global disasters and things like that? A new phone. Right? I'm on the aftermath, if you will, of the iPhone 6, or what will, again, 2 years from now, iPhone 7 and 8 and 9. What's the biggest thing? What keeps people intense at night, lined up outside of building? A new cell phone, because we have to be. I'm getting on a soapbox. I'm not going to go there, but you can see we need addresses in our current network address translation Band-Aid to make IPv4 work a lot longer than it should have, is starting to come off, because we need even more private addresses than we have available to us nowadays. So what are we doing? IPv6, the transition is happening. We're moving from 4.2 billion into, I can't even say the number. You've probably seen it before. It's just lots of Google's, gobbles, whatever of IP addresses that are available. Kinds of communications the organizations are using. Unicast, one-to-one. I'm sending from my iPhone to a server to share files, right? One-to-one communication. Multicast, one to a group, to where I can have for instance, a server streaming music in my organization, like Music on Hold, to a whole bunch of IP phones that are tuning into that if they ever put somebody on hold. So that way you send one stream out instead of all these individual streams to phones that are trying to play hold music. It's a lot more efficient to use multicast traffic like that. Or broadcast, the best of the world and the worst of the world. Broadcast has to happen to make our networks work, like ARP requests, figuring out what MAC addresses map to IP addresses, like DHCP requests to get an IP address in the first place, like the list goes on of broadcast traffic that's out there. So broadcast traffic needs to be there for networks to function, but also is the main reasons we start dividing up networks, because it gets too congested due to broadcast traffic. And that's what they're out to fix with IPv6. Now, I just put this on there to talk about. It's not a communication type. IPv6, first off, moves into 128-bit addressing, CIDR notation, and this right now is probably in the review material of CCNA. You've seen this before. Kinds of communication, one-to-one, one to a group, and now this new kind, which actually, it's around in IPv4, but we're kind of breaking and bending the rules to make it happen. Anycast traffic. Essentially, anycast means one, let's see, how can I describe it? One IP address assigned to many devices. We're actually using Anycast right now for services like DNS. For instance, if you look at Amazon Web Services and you host your DNS with them, they actually give you a ton, probably into the hundreds of DNS servers that they have worldwide. And when somebody does a DNS lookup, let's say you're hosting the domain cbtnuggets.com on AWS, when somebody looks up your domain name, they'll actually go to the DNS server closest to them. Well, how does it figure that out? How does it figure out which DNS is closest to you? Well, what they do is they assign multiple, or essentially the same IP address, let's just say 1.1.1.1, to multiple devices. Now, I know normally you're like, you can't do that. Well, in the BGP world, you can, because BGP supports having the same network through multiple paths. And so BGP, which we're going to talk about a lot in this series, is used to essentially take these 1.1.1 IP addresses, or I should say DNS networks, and advertise them out to all the different service providers. So when you and I are sitting there going, hey, who's cbtnuggets.com? It's going to look up using the 1.1.1 server closest to you, or I guess more specific, closest to your service provider, because there's all these duplicate 1.1.1s all over the place. That's been formalized in IPv6. Right now we only use it for very like UDP based traffic, because you can't have sessions that move between anyway, it's just bending the rules in IPv4. It's very formalized in IPv6. Now let's talk about this one. I don't want to get into all the different IPv6 address types, because it can be a longer discussion. I just want to bring it up to make a big point on how IPv6 works. In IPv4, you get an IP address, right? That's it. To have two IP addresses is weird. It's an anomaly, like, oh, you've got some kind of magic you're doing, or a specialized need that you assign two IP addresses to the same PC or server or whatever you're assigning that to, right? At least from a server perspective. In the IPv6 world, it's going to be the norm. Essentially, you get your IPv6 global address, essentially the one that works on the internet, and then you get your IPv6 link local address. Closest thing I can compare it to is the 169.254, if I could write it, subnet of yesteryear with IPv6. Everybody that sees this address knows something has gone wrong, usually, because that is an auto-generated address when a device can't get one via DHCP. Well, the reason that they have those addresses is to allow local communication between devices even if there's no DHCP server. Well, in IPv6, that's become the norm, meaning you'll have one address that you use to talk to the world, and you'll have another address that you use to talk to things on your local subnet. The reason it's important is we're about to embark into the route series. We're going to be talking about a lot of neighbor relationships between routers, exchanging, for instance, routes via OSPF or BGP, and all the different protocols we can use. Most of the time, they'll be talking using their link local addresses, and you'll see neighbor relationships form using an IPv6 link local address between devices. So there is your Technology Connecting Offices overview. I even hesitate to call them WAN links anymore, because fiber optics has brought the world so much closer together. At least when you can travel at the speed of light, I suppose you are closer together, right? So we've seen that big picture, looking at direct connections to packet switch, to DMVPN, to Metro Ethernet, MPLS, all the different ways that we can connect our offices together, which is key to understand, because it plays a role in architecting how we design our routing protocols and how we lay that out to work well together. We then saw the IPv4 and IPv6 logical addressing, again, big picture overview of the communication types, but laying that foundation that we need to build upon as we dive deep. I hope this has been informative for you, and I'd like to thank you for viewing.